Friends, I would like to explain to you double integrals from scratch. I'll first introduce to you very simple double integration problems where the limits are provided. So the job is to just understand the order of integration and then evaluate. So let's begin with the first problem. Integral 0 to 3, integral 0 to 2, 4 minus y squared dy dx. One should understand that when the limits of integration are constant over both the variables, you are integrating over either a rectangular region or a square. In this case, you can observe that x varies from 0 to 3 and y varies from 0 to 2, which means that we are integrating over a rectangular region. So instead of getting into the geometry, let me directly show you the procedural steps of performing this integration. We will stick to the order given. Integration with respect to y first, followed by integration with respect to x. I is equal to integral 0 to 3. The integration of 4 with respect to y is 4y. The integration of y squared with respect to y is y cubed by 3. The limits are 0 to 2. So you get 4 times 2 8 minus 2 cube is 8 by 3 dx with lower limit not contributing anything. So you have 0 to 3. Simplify this, you will get 16 by 3 dx. 16 by 3 is a constant. The integration of dx is x from 0 to 3. So this will give us 16 by 3 times 3 and the output is 16. So what we understand from this very simple example is that when you have limits of integration as constant, the job is practically very simple, provided you are able to handle the integration. What this output means can be discussed later when we understand what is the function given to us. I will now take you to the next example where we have variable limits on the inner integral. So let us consider 0 to 1, 0 to square root of 1 plus x squared dA by x squared plus y squared plus 1. So we know that dA is the area element, and if you look at the limits of integration, the inner limits are functions of x, which means that the region of integration is definitely not a square or a rectangle. So when you have inner limits as function of x, then dA should be transformed into dy dx. Let us recall that when you have a region and you are making a mesh with horizontal and vertical lines, you get an area element dA, which is width times height. So if this is delta x and that is delta y, so dA would be delta x into delta y or delta y into delta x. One can choose any of these two, but in this specific case, when you have inner limits of functions of x, they correspond to the limits for y. So let me make it more clear. Y limits are 0 to square root of 1 plus x squared. Then x limit will be 0 to 1. Write dA as dy dx. Then you bring together x squared plus 1. Then write plus y squared. So this x squared plus 1 will act as a constant with respect to y, because that is the first variable we are going to use for our integration. But you must know how to handle this equation. So I'll write one more step which will help us think clearly. So write the x squared plus 1 as the square of square root of x squared plus 1. And I hope now you have recognized that this is in the standard form. If square root of x squared plus 1 is a constant like a, then this integral, that part of the problem, appears something like dy by a squared plus y squared, which when integrated uses 1 by a tan inverse y by a. So a in this problem is square root of x squared plus 1. So I will be getting 0 to 1, 1 by square root of x squared plus 1, tan inverse y by square root of x squared plus 1. Limits 0 to square root of x squared plus 1 dx. So you submit the limits for the variable y, and you will get 1 by square root of x squared plus 1 into tan inverse square root of x squared plus 1 by square root of x squared plus 1 gives us 1 after calculation minus tan inverse 0 dx. Tan inverse 0 of course is 0, whereas tan inverse 1 is pi by 4. So pi by 4 can be extracted out. So you are now have to integrate 1 by square root of x squared plus 1, which is log x plus square root of x squared plus 1 within the limit 0 to 1. So you have pi by 4 times log of 1 plus 1 is 2 under root minus log of 0 plus 1. Log 1 reduces to 0, and therefore your output will be pi by 4 log 1 plus square root. So this is how, when you have variable limits, and in particular when the inner limits of integration are functions of x, the order of integration is dy dx and not dx dy. I hope you can now guess what should be the order when the inner limits are functions of y. So then the order would be dx dy. So let me take this example after this one. This is my third example where, as I tried to explain earlier, we'll have inner limits as functions of y. So the area element dA has to be written as dx dy, because in the previous case when you had inner limits as functions of x, dA was written as dy dx. So one must be extremely clear about these orders. So let me show you how to go about this question. So you can observe that the inner limit, of course this is 0, but we got an upper limit which is a function of y. So this dA will be written as dx dy. So accordingly, we will have 0 to 1, 0 to y squared, 3y cubed, e power xy dx dy. Integration with respect to x will take place first, which means these are the limits for the variable x, followed by integration with respect to y. So these will be the limits for the variable y. So now, let us analyze this function. With respect to x, 3y cubed remains a constant. So we will have integral y is equal to 0 to 1. 3y cubed remains constant. Integration of e power xy with respect to x will be e power xy divided by y. Limits 0 to y squared for the variable x. So we'll have y is equal to 0 to 1. One of the y's will get cancelled here. We'll have 3y squared e power. Y squared will replace x. Therefore, we'll get e power y cube minus e power 0 dy. So this would give us integral 0 to 1, 3y squared into e power y cube minus 1 dy. So let us carefully handle the situation. I will write I as I1 minus I2. Where you have one integration that will handle the first part, that is what I call I1 minus the second. So let us talk about I1. I1 is integral 0 to 1, 3y squared, e power y cubed dy. I can easily observe that the derivative of y cubed, which is 3y squared dy, is present. So we'll make a simple substitution. Y cubed is equal to u and take differentials on both sides. 3y squared dy is equal to du. But there should also be change in limits. Let us start with y is equal to 0, which is the low limit, and work out the corresponding u limit. It will be u is equal to 0. Similarly, when you take the upper limit, y is equal to 1, u produces 1 cubed, which is 1. Effectively, the limits have not changed, but the variable has changed. So I1 is nothing but u is equal to 0 to 1 e power u into du. That's a straightforward integration. And we get e minus 1. So I1 produces e minus 1 as the output. Let us see what happens to I2. I2 is integral 0 to 1, 3y squared into 1. That is 3y squared dy. This is straightforward. 3 times y cubed by 3 from 0 to 1. 3 goes off and we will get 1 minus 0, which is 1. So, back to equation number 1, that gives us the final output. I is equal to I1 is e minus 1 producing e minus 1. So we have learned a little bit from these last two examples. When the inner limits are functions of y, the order of integration is dx dy. And the previous example taught us when the inner limits are functions of x, the order of integration is dy dx. Of course, when the limits are constants on both the integrals, you have to respect the order of integration that is given in the problem. So one of the important things to understand now onwards is how do these limits, inner limits, functions of x or functions of y generated? What is the genesis of this problem? For that you must understand the geometry of regions. That is what I'll be taking up in my next lecture. Thank you.